All right, now, compounds that are aromatic. So here are our rules and our illustrative example of benzene. Now, let's consider some other molecules. We've already seen cyclobutadiene. It had 4 N pi electrons, so it was anti-aromatic. Okay. Let's consider some others. This is cyclooctatetraene. Now, what we do first is we consider the hypothetical. In a planar structure, everything's sp2. If it were fully planar, it is monocyclic. In that case, if it were planar, it would be fully conjugated. Then the question is how many pi electrons, and of course with 4 double bonds, we have 8 pi electrons, so it is anti-aromatic also. We can continue to grow these bigger and bigger. We can also look at anions. Let's look at a couple of these. So the first one we'll take up is this compound. Now, we're going to start here with cyclopentadiene. So is cyclopentadiene aromatic or anti-aromatic? Well, is it planar? Oh, we have 4 sp2 carbons, and then we have this other one, so it probably could be pretty close to planar. It's monocyclic. Is it fully conjugated? Well, I can certainly push the arrow like this, but this one, well, we can't really do that, right? Because that's an sp3 carbon, so it is not fully conjugated. So it is neither anti-aromatic nor aromatic, and hence my term, neither. Your textbook uses something else, it's fine, whichever one. It's neither aromatic nor anti-aromatic. It's just a diene. And we would expect, because it doesn't fit into either of those categories, it'll react like cyclohexadiene, butadiene, any other diene compound. And that's what, in fact, we see. Now, let's consider if we deprotonate cyclopentadiene. If we deprotonate cyclopentadiene, we have the cyclopentadienyl anion. If we consider this, 1, 2, 3, 4, 5 atoms, of course these 4, 1, 2, 3, 4, are sp2. But what about atom 5? Well, of course, conjugation imparts stability. So if we can have this be fully conjugated, we get a resonance formed here. The anion has moved, and now, of course, it doesn't matter where I put the lone pair or the charge, inside or outside the ring. That's arbitrary. The molecule doesn't know where I draw it. So this molecule looks as though it's fully conjugated, and there are in fact a number of additional resonance structures I could draw for this molecule. You should draw some more to practice your resonance forms. I'm not going to draw them here in the lecture. So with this observation, here's what was atom 5, so clearly it is sp2, and remember, atoms don't change hybridization in resonance. So if atom 5 is sp2 here, atom 5 is also sp2 there. So this molecule is in fact fully conjugated, it's monocyclic, and it's planar. And then how many pi electrons? Well, all of these electrons, the 4 electrons in the double bond plus the 2 in the lone pair, give me 6 pi electrons. So this is an aromatic anion. Okay, and this is an example of an aromatic anion. And so we see lots of chemistry for this kind of compound, bonds to metals like benzenes and various other things. So we have neutral molecules that can be aromatic or anti-aromatic. We have anions. We can also have cations. Let's consider the following. This is cyclopeptide triennyl cation. What I hope you see pretty quickly now is, of course, this is also conjugated, right? All the way around the ring. We could continue this process. And that would give us the cation then over here. You should draw, I'm going to leave it as an exercise for you to draw that. Contact me during office hours if you have questions or are struggling with resonance forms. So that means all of the atoms are sp2 hybridized. It's planar, it's monocyclic, it's fully conjugated. Now how many pi electrons? Let me go back with a different color here to emphasize. Here's one pi bond, the other pi bond, a third pi bond, and then this is a carbocation. How many electrons does the carbocation have in its p orbital? Remember, carbocation is sp2 hybridized. It has a vacant p orbital, so it doesn't contribute any pi electrons. So I have 2, 4, 6 pi electrons. So this is aromatic. We can have neutral molecules that are aromatic or anti-aromatic. We can have charged molecules, anions or cations that can be aromatic. And then I'm going to slip one more in here. Let's consider this. This is the cyclopentadienyl cation. Again, apply our 4 criteria. What do you think about it in terms of aromatic, anti-aromatic, or neither? Well, I hope you are now seeing rather quickly that this molecule would be anti-aromatic. Because if we consider the hypothetical planar, all the atoms are sp2 hybridized, it's monocyclic, it would be fully conjugated. I can push the arrows like this. But it would have 4 pi electrons. That's an anti-Huckel number, and so this is an anti-aromatic cation. So the charge doesn't impart aromaticity or anti-aromaticity. So don't look at just the charge. We have to count the pi electrons, consider the geometry constraints of the molecule, and then we can make the determination if a molecule is aromatic or not. And of course that has huge impact on its stability and its chemical reactivity. And these are very important properties to be able to predict. All right.